Hi everyone. In this video, I'm going to go through 2024 Step 3 Question 7. And I guess the point of this video is I don't want to give you an overly polished solution, the kind that you might find in the mark scheme. I want to kind of give you sort of step-by-step intuition. I want to give you the sense of like how I would approach this question if I were in the exam, and also how I would explain the solution to a tutee who had maybe thought about some of it but was still stuck on some of the details. So for that reason, I recommend that before each part, you pause the video, have a go at the question, so that you can get the most out of going through it. So in this question, basically, you're given these two infinite series, f of n and g of n, indexed by the positive integers. And so it's quite funny. It says, you need not consider issues of convergence. When I was in sixth form, I didn't know what convergence was, so that wasn't really a problem for me. But if you do know what convergence is, maybe you can leave a comment as to how you know that the two series converge. But that's just an aside. You don't need to know that for the exam. So what you have to do is first you prove these upper and lower bounds on f and g. And then you have to do this weird thing involving e. It seems like parts 3 and 4 are sort of not related. It's a kind of different thing. And then the n part showing that e squared is irrational, that's kind of that's sort of the kind of climax of the question. And often step questions do this kind of thing where the last part is a very cool result, which if that was the whole question, maybe it would be very difficult to do. But because you have a lot of scaffolding, you kind of walk through an interesting proof overall. Okay, so then I think what we'll do is we'll get started with the first two parts. Okay, so for the first part, you need to give an upper and lower bound for this series, f of n. So the lower bound is, I think, quite straightforward, f of n being strictly positive, because it's just a sum of strictly positive terms, so it itself must be strictly positive. For the upper bound, it says by considering a geometric series. So you do have to do it that way, otherwise you won't get the marks. But let's see. Okay, so this kind of looks sort of like a geometric series, except instead of sort of timesing by a common factor, you times by something that's sort of close-ish to the common factor of 1 over n plus 1. In fact, it's actually smaller. So what you want is, you can say f of n is strictly less than 1 over n plus 1 plus 1 over n plus 1, and then the 1 over n plus 2 is smaller than the 1 over n plus 1. So this is altogether smaller than 1 over n plus 1 squared. And then the next term is strictly smaller than 1 over n plus 1 cubed, and so on. But then, okay, now this is a geometric series. And you know the sum to infinity of a geometric series that converges is a over 1 minus r. So this is equal to 1 over n plus 1 over 1 minus 1 over n plus 1, which is 1 over n plus 1 minus 1, which is 1 over n, which is what you wanted. Okay, now to get the same bounds on g, slightly harder. So let's just draw a quick diagram just to get some intuition. So okay, so we need to show it's strictly between 0 and 1 over n plus 1. So if I maybe draw a number line like this, going from 0 to 1 over n plus 1, then if we consider each term of the sum, we sort of start with 1 over n plus 1, and then we don't quite go down all the way to 0, because this 1 over n plus 1 is times by a factor of 1 over n plus 2. So we say we go sort of like this up to this point here. And then similarly, we go back up again, because we add this term here. But we don't go back up all the way, because the 1 over n plus 1 times 1 over n plus 2 is times by a factor of 1 over n plus 3. So we end up going maybe, say, up to here. And this isn't drawn to scale, by the way. And then, you keep going. And so you end up maybe somewhere in the middle, like there. Okay, so that's not going to suffice in the exam, just to draw that diagram and to give that explanation. Especially because it says we need to compare consecutive terms. So let's go ahead and do that. So to get the upper bound, we sort of want to end up in the same. Sorry, to get the lower bound, we want to end up in the same place where we did for f, where we have just a sum of strictly positive terms, which is therefore strictly positive. So what we can do then is by the argument I just made now, I can group up the terms basically like this, right? And then the next term here will be a 1 over n plus 1 up to n plus 4. So then now that's a sum of strictly positive terms, which is strictly positive. So I'm not going to write that out again, but I will write out the upper bound. So we also want to use the same idea, Because, so the way we did it intuitively is that we started off at 1 over n plus 1, and then we showed that we go down by a strictly positive amount in total, right? And then that's basically why the upper bound is 1 over n plus 1. So in writing that out sort of in terms of in the way they want you to do it in the question, I can say that g of n is equal to 1 over n plus 1 minus. So now the goal is to get a big bracket where everything here is strictly positive, and then that is going to give us the upper bound. So I can say this is 1 over n plus 1 times n plus 2, and then now this used to be a plus, but it's now a minus 1 over n plus 1 times n plus 3. And then there's now a plus, and then there's the n plus 4 term, and so on. So you see, now what we can do is to show that the goal basically is to show that this is strictly positive, but then that's just the same argument as for the lower bound, because we can just group up the terms. I'll do this in white, kind of like this, right? And then the n plus 4 and n plus 5 term, and so on and so forth. Okay, so now for the next part, we move in a slightly different direction. We need to show that these random expressions involving f, g, and e are integers. And what I would say to start off with is that the only definition we know for f and g involve infinite series. So it's going to be pretty much impossible to do this part unless we can also get the terms involving e as infinite series. So this is something now, it might be on the A-level formula booklet, but you should know it off by heart for STEP, which is the series expansion for e to the x. And this is that for all real numbers x, e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. And in fact, actually, once you start studying analysis and so on in first year, some textbooks or some kind of courses, they actually define the exponential function like this, and then they can prove all the other properties by kind of working from this definition. So that's something to bear in mind. That this is basically a very important fact about e to the x. And okay, so anyway, we're going to use it in this case. So I think the only sensible thing to do really is just to write out the expressions and hope that something works out. So okay, for example, we can say, okay, 2n factorial times e minus f of 2n. Okay, so this is equal to 2n factorial times, and I'm just going to write out what e is. So this is 1 plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial, and so on. Okay, and what might be sensible to do is to think, okay, so we've times by 2n factorial, and then we also want to eventually show that some stuff are integers. So let's just go up to 1 over 2n factorial, and then let's just maybe write one other term, the next term after that, and then just do the ellipsis. Okay, and then minus f of 2n. So I have the definition of f of n over here. So, okay, so this is minus 1 over 2n plus 1. I'll do this in brackets. Plus 1 over 2n plus 1, 2n plus 2, plus, and then, yeah, and so on. Okay, so we need to show that this is an integer. So the first few terms, that we get 2n factorial, and then we also, so actually up until basically this point here, we sort of get integers, right? Because we have sort of 1 over something less than 2n factorial times by 2n factorial. So the terms are gonna all the terms on the denominator are gonna cancel out. So we're gonna be left with integers. So we only have to basically worry about what's after this. So what I can do is, let's just say that this is equal to some x, right? Where x is basically 2n factorial. Maybe I should do over here. I'll do a different color. Yeah, so where x is basically 2n factorial plus 2n factorial over 1 factorial all the way up to 2n factorial over 2n factorial. This is just for the sake of a notation that I've for the sake of convenience, I've written it like this. Okay, and then there's also a plus, and this is going to be 2n factorial over 2n plus 1 factorial, which is 1 over 2n plus 1. This looks suspiciously similar to to what's over here. So we're going to hope that they cancel out. And then the next term is 2n factorial over 2n plus 2 factorial, which is 1 over. This is a plus. Sorry, this is 1 over 2n plus 1 times 2n plus 2. and so on. And indeed, that just perfectly cancels with what's over here. And so we're just left with this quantity x. Oh, no, why is it doing that? Yeah, sorry about that. So this is so this is just equal to our quantity x, which is indeed an integer. And then there's a similar argument that we're going to do for the term involving g. I will write it out just for the sake of completeness, and also just to make sure it's really clear what we're doing. So here we have 1 over e instead, which is of course e to the minus 1. So instead, what we have is so this is going to be 2n factorial. And then now, if we just use this definition of e to the x, this is going to be 1 minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial. And again, let's go up to 2n. So remember, so 2n is even, so it is actually going to be a plus 1 over 2n factorial, and then a minus 1 over 2n plus 1 factorial, and so on. And then the other term here is g of 2n. Which is what we're doing. Oh, we're adding g of 2n. Yeah. So this is plus, and if I look at the definition, 1 over 2n plus 1 minus 1 over 2n plus 1, 2n plus 2, plus, and so on. Okay. And then, okay. So as before, we have a bunch of integers. So when we go up to 2n factorial, this term here, we're going to have integers. So let's just call that the first bit y, and then we're left with 2n factorial times 1 over 2n plus 1 factorial. So I'll just do this in one bracket here. So this is now a minus 1 over. And actually, in fact, maybe it's easier if I do a minus here. Yeah. So this is a minus 1 over 2n plus 1, and then the next term here. So it would have been a plus, if I just put it here, a plus 1 over 2n plus 2 factorial. And then that's now times by the 2n factorial. So this is now a minus because the minus cancels with a minus here. So 1 over 2n plus 1, 2n plus 2. And yeah, you can see that that's going to cancel with what's over here. And so we're just left with y, which is an integer. Okay, so now for this part, what you're going to do is, so you've shown that a bunch of stuff were integers in part 3, and then now you need to show that more things are integers, and then, okay, so you're just going to do what you did, and you're going to try to apply what you did in part 3, right? So you have that if QE equals P over E for some positive integers P and Q, then this quantity here is an integer for all positive integers N. Okay, so what you know so far is that, let's first fix a value of N, a positive integer N, because we want to show it's true for all N. And then we know then that 2n factorial times E minus f of 2n, well, that's equal to some A, which is an integer. And then we also know that 2n factorial times 1 over E plus g of 2n, that's equal to some b, which is also an integer. What we'd like is to get rid of the e's and actually also get rid of the factorial signs as well. And we also want to introduce p and q, so that I think the only sensible thing is just to let's just times by q, for example, and see what happens. And it is going to be, so as in let's times the top by q, and the first one by q and the second one by p. So if we do that, then we end up with, so I'm actually just going to sort of overwrite it here. So I'm just going to put a q here. And then this is qf of 2n, and then this is qa, which is of course still an integer. And then over here we have a p that goes here and here and here. And okay, this is great. This looks like pretty much what we want, because we know that QE equals P over E. So then now if what we do is we just times the top bit by minus 1, and then we just add the two together, then we're going to be done. We're going to get that's QF of 2n plus PG of 2n is equal to PB minus QA, which is an integer. And I'll just write that again for the sake of completeness. Okay, nice. Okay, so for this last part, you have to show that e squared is irrational. And it might not be immediately clear what you are going to do, but let's think. So maybe up to this point, every time you've seen a proof that a real number is irrational, in fact, you might have only even seen say that root 2 was irrational. And you know that that was done by contradiction, right? So suppose root 2 is equal to p over q, where p and q are positive integers that are co-prime, and then you sort of do some multiplication and squaring or whatever, and then you get a contradiction. So let's try and do something similar in the case of e squared. So we have, suppose e squared was equal to p over q. So we don't really care about them being co-prime for the moment, but just the fact that they're positive integers, that's the key here. Because then what I can now do is, so firstly, you can observe this looks quite similar to part 4. So let's just now rearrange to get QE equals P over E. And now we're exactly in the situation of part 4. So, okay, we're saying that suppose that E squared was irrational, then what we can now conclude is that QF of 2n plus PG of 2n is an integer for all positive integers n. Okay, so what we need to do is we need to get a contradiction to do with that. So the contradiction, I suppose, is going to come from choosing a specific value of n. That kind of means that that this expression here just obviously can't be an integer. Okay, so at this stage, again, you might get stuck. You might not really sure. You might not be clear which values to pick for n, and also how the contradiction is actually going to arise. But then, okay, my sort of golden rule for step questions is that every time you get stuck, you should always try and see, can I use something from the previous part? So in this case, you've already given upper and lower bounds on f of g, ffn and g of n. So that might come in handy in this case, because if you wanted to show that if you say you had some nice value of n, then you could then try and get an upper bound that was so tight that it meant that this expression here basically couldn't be an integer. So let me just write that out properly. So we know then that from the first and second parts that qf of 2n plus pg of 2n. Well, okay. Firstly, they're both strictly bigger than 0 because we have the same lower bound for both f and g, and then they're strictly less than. So f of n was less than 1 over n. So this is now q over 2n, and then g of 2n, that's going to be strictly less than 1 over 2n plus 1, but that's also strictly less than 1 over 2n. So I'm just going to write this as p over 2n as well. So this is p plus q over 2n. Okay, so we've supposed that e squared is irrational, and we've got then that this thing in the middle has to be an integer. So the way we can get the contradiction is to make p plus q over 2n less than 1, right? Because then in that case we know there's no positive integer, there's no integer between 0 and 1. So that's that's our contradiction. So what value is going to give us that? Well, why don't we just try p times q? So if we put then n equals p times q, then we're going to get that qf of 2n plus pg of 2n. Well, that's strictly between 0 and p plus q over 2pq, which is equal to, so this is a half times 1 over p plus 1 over q. But because p and q are both positive integers, then we know then that this here has to be, so we know then that, okay, so we know that they're not both equal to 1, p and q, right? Because we know that e squared isn't equal to 1. So then otherwise that means then, so we can then conclude that this expression here is strictly less than 1. And then that gives us our contradiction. So I'll just do a contradiction sign. So therefore our original claim that e squared was rational must be false, and so indeed e squared is irrational. Okay, so I hope now you're able to see that it wasn't too bad of a question overall. I think the key bits were basically spotting the series expansion of e to the x, and then the same trick for all the step questions, which is to refer to the previous parts when you get stuck. And then, yeah, with those things in mind, it sort of proceeded somewhat smoothly. But yeah, so I mean, hopefully you found this useful, and if you did, then please do consider checking out the rest of my website. And if you're interested in tutoring, then I'd be happy to help you out and have a quick chat to see what you're working towards. And yeah, so anyway, thanks very much for watching, and I'll see you in the next one.